Kinetic molecular theory forms the basis of our study on gases. And the kinetic molecular theory has 6 points. Number 1, a gas is comprised of extremely small particles called molecules, or in some cases atoms if you're looking at like a noble gas. The molecules are usually separated by great distances, and they occupy only a small fraction of the total gas volume. So they're assumed to be point masses. Their body is so small its size can be ignored. There are assumed to be no intermolecular forces on those gas molecules, so they move independently of each other. They are not attracted or repelled by each other. Number 4, the molecules move constantly and randomly through a gas in straight line paths, and so they will undergo frequent collisions with one another in the walls of their container. Number 5, collisions between molecules are elastic. Individual molecules may gain or lose energy, but in a large collection of molecules, the total energy remains constant. Number 6 is important. I'll put a star by this because you will see this again. The average kinetic energies of molecules of different gases are equal at a given temperature. The average kinetic energies of molecules are equal. Now, if the temperature changes, the kinetic energy changes of those gas molecules. Kinetic molecular theory can explain the properties of gases. Now, the pressure exerted by a gas upon the walls of the container is caused by the gas molecules striking the walls and depends on 2 factors. Put a star by this because these 2 factors are important in determining pressure. Pressure is determined by the number of molecules that hit the wall per time and the force with which those molecules strike the walls. If I have the volume of a sample of gas, it doubles the pressure. So from 1 to 2 here, basically I have halved the volume. Now the pressure is doubled because more molecules are striking the wall per unit time if the temperature remains constant. The kinetic energy has not changed, so more molecules are striking the walls of the container per unit time. If I double the absolute temperature, it doubles the kinetic energy, and the increased vigor of collision doubles the volume if we have constant pressure. So if I double the temperature, I double the kinetic energy, so there's more collisions, they're hitting with more force, and that's going to double the volume at constant pressure. A sample of gas can be compressed because the sample consists mainly of empty space. Again, those molecules take up very little space. They are point masses. And so gases can be compressed. If the intermolecular attractions between gas molecules were large, they would congregate in a pool at the bottom of a container as a liquid. And so we know that there are very few intermolecular attractions between gas molecules. The property of diffusion, which is spreading out, is explained by the fact that gas molecules move with high velocities, and the rates of diffusion, how fast they spread out, are explained by molecular collisions. We're not going to worry about number 8 here, translational kinetic energy, so you can kind of cross off all of 8, which is A, B, C, and D. Just cross off all of number 8 there. You will not be tested over translational kinetic energy. Last gas law we'll look at is called Graham's law. Because gas molecules are in constant, rapid, random motion, they diffuse quickly, which means they spread out quickly in any container. If gas molecules are allowed to escape from their container through a tiny hole, this process is known as effusion. It's like when a helium balloon loses air, it's because it's losing the helium as the helium molecules escape through the tiny holes in the balloon. The relative rates of effusion or diffusion of 2 gases can be derived from the fact that at a given temperature, the average kinetic energies are equal. I'm not going to go through the derivation here under letter C. It's not really pertinent to what we are doing. So the rates of diffusion are directly proportional to the average of velocities, and molecular masses are equal to the masses of the molecules. So Graham's law looks like this. The rate of gas A divided by the rate of gas B is inversely proportional to the square root of the molar masses. So if I want to compare the rates of effusion or diffusion of 2 gases, A or B, this is the equation for Graham's law. So this first problem here says, what are the relative rates of diffusion of methane and sulfur dioxide? Since methane is listed first, I will put that in the numerator. That's gas A. Sulfur dioxide would be gas B. I want to know the relative rates of diffusion. So we're going to put the molar mass of SO2 up here. Because they're inversely proportional, CH4 goes in the denominator. We're going to plug in those molar masses. SO2 has a molar mass of 64 grams per mole. CH4 has a molar mass of 16. 64 over 16, square root, comes out to 2. We always have to have a comparison here, so it says what are the relative rates of diffusion? I always compare it to 1. And what that means is CH4 diffuses twice as fast as the SO2. Smaller gases diffuse quicker, and that makes sense. So CH4 would diffuse twice as fast. It is a smaller molecular mass gas. I can get the molecular mass of an unknown also using Graham's law. Here's how we'd set that up. We want to know the molecular mass of the unknown gas, and we know that hydrogen effuses 4 times as quickly. So my setup would look like this. Rate of H2 over rate of my gas X, we'll call it. Inversely proportional, so the molar mass of gas X goes up here. The molar mass of hydrogen goes down here. I know hydrogen effuses 4 times as fast, so I'll say 4 over 1 is equal to square root mx. Molar mass of hydrogen is 2. In order to get rid of that square root sign, we'll kind of come over here. We'll square both sides. So square both sides gives you 16 over 1 equals mx over 2. So the molar mass of gas X, the unknown in this case, 32 grams per mole. So Graham's law can deal with diffusion, which is spreading out, or effusion, which is escaping through a tiny hole. According to kinetic molecular theory, no attractive forces exist between gas molecules, and the volume taken up by the gas molecules is negligible. However, real gases have weak attractive forces between them, and the molecules do occupy a small part of the volume. Real gases deviate from ideal behavior, especially at low temperatures and high pressures. However, with the temperatures and pressures we will be using, it is perfectly okay to use the ideal gas law, PV equals nRT, for real gases.